Hey everyone, I am Archie Jaipuria. Today, in this presentation, I'll analyze electricity demand data using Fourier analysis to understand the structure of the signal in the frequency domain. Electricity demand fluctuates throughout the day due to human activity, weather, and economic factors. The dataset used in this project contains hourly measurements of electricity demand over time. The goal of this study is to analyze the structure of the signal and understand its underlying behavior using Fourier analysis. Specifically, we want to examine the frequency components of the signal and interpret what they represent in the real world. The electricity demand dataset is sampled once every hour, so it can be represented as a discrete time signal. Mathematically, we write the signal as x of n, where n ranges from 0 to n minus 1. Here, x of n represents the electricity demand at time index n. Now, since the sampling interval is 1 hour for us, delta t equals to 1 hour, this gives us a sequence of demand measurements over time. Now, before performing Fourier analysis, we remove the mean of the signal. This is done using xc of n is equals to x of n minus x bar, where x bar is the mean of the sample data. The reason for this step is that the mean corresponds to the DC component or the zero frequency. By subtracting the mean, we focus on the oscillatory variations in demand rather than the baseline consumption level. Now, the central mathematical tool used in this analysis is the Discrete Fourier Transform or the DFT. The DFT decomposes the signal into a sum of complex sinusoidal components. X of k is equals to summation of xc of n into e power minus j 2 pi k n by n. Here, each coefficient x of k represents the contribution of a particular frequency in the signal. In other words, instead of viewing the signal as a function of time, we can interpret it as a combination of different frequencies. Each Fourier coefficient corresponds to a frequency fk is equals to k by n delta t. Since the sampling interval is 1 hour, this simplifies it to fk is equals to k by n. This transformation converts a signal from time domain x of t to frequency domain x of f. This allows us to analyze which frequencies dominate the signal. Now, to determine the strength of each frequency component, we compute the amplitude spectrum A of k is equals to mod x of k. Plotting the amplitude spectrum would reveal which frequencies contribute most strongly to the signal. Large peaks in the spectrum would correspond to dominant periodic behavior. Now, I'll demonstrate the computational implementation in Python. First, the dataset is loaded and the date time column is converted into a proper time format. We then sort the data to ensure that the signal is ordered chronologically. The electricity demand values are stored as a numerical signal for analysis. Next, we plot the electricity demand in the time domain. As we can see, the signal fluctuates significantly and appears somewhat irregular. Although we may suspect that daily patterns exist, they are not clearly visible in this raw plot. This motivates the use of Fourier analysis. So, we then compute the Fourier transform using the first Fourier transform algorithm. The FFT efficiently computes the discrete Fourier transform of the signal and produces the set of Fourier coefficients. From these coefficients, we compute the amplitude spectrum. This plot shows the amplitude spectrum of the electricity demand signal. The horizontal axis here represents frequency and the vertical axis represents the strength of each frequency component. Here we observe distinct peaks at specific frequencies. Large peaks corresponds to frequencies that strongly influence the signal. However, frequency is sometimes difficult to interpret directly. So, instead of frequency, we can express the spectrum in terms of period. Here, I convert frequency into period using the relation t is equals to 1 by f. This allows us to interpret the spectrum in terms of time cycles rather than the frequency values. Now, for example, if the spectrum shows a peak at 24 hours, it indicates a daily cycle in electricity demand. Here, in this plot, we observe peaks corresponding to approximately 24 hours, which represents the daily demand cycle, and 168 hours, which represents the weekly activity cycle. These periodic patterns correspond directly to human behavior, such as work schedules and weekly consumption patterns. To automatically identify dominant frequencies, I use a peak detection algorithm. This function scans the amplitude spectrum and identifies frequency with large amplitudes. By converting these frequencies into periods, we can directly interpret the dominant cycles present in the signal. In this dataset, the detected peaks correspond approximately to daily and weekly demand cycles, again which reflects the human activity patterns. Now, we can also examine the distribution of signal energy across frequencies. The energy associated with each frequency component is Ek is equals to mod xk whole square. So, next, I examine how the signal's energy is distributed across frequencies. Plotting this distribution helps us understand where most of the signal's power lies. In this plot, we observe that most of the signal energy is concentrated in low frequency components. This indicates that electricity demand changes gradually over time rather than exhibiting rapid oscillations. High frequency components correspond mainly to random fluctuations and noise. Finally, I investigate how sampling resolution affects the Fourier spectrum. Here, I downsampled the signal by keeping only every third data point. This effectively reduces the sampling rate of the signal. After downsampling, I recomputed the Fourier transform and plotted the new spectrum. We observed that reducing the sampling resolution changes the frequency representation of the signal and may distort some frequency components. This illustrates an important concept in the signal processing, that the accuracy of Fourier analysis depends on adequate sampling resolution. Using the analysis above now, we can extract several insights. First, Fourier analysis reveals hidden periodicity, particularly the daily and weekly demand cycles. Secondly, the majority of signal energy is concentrated in low frequencies, indicating that electricity demand evolves gradually. Third, the smaller frequency components represent noise and short-term variations caused by weather and other unpredictable factors. Thus, the frequency domain provides a structured interpretation of what initially appears to be a complex signal. In conclusion, this study demonstrates how Fourier analysis provides a powerful framework for analyzing real-world signals. Although electricity demand appears irregular in the time domain, the frequency domain reveals clear periodic patterns driven by human activity. By decomposing the signal into its frequency components, Fourier analysis allows us to identify dominant cycles, understand energy distribution, and interpret the underlying behavior of the system. This illustrates how thinking in the frequency domain reveals the structure that cannot easily be seen in the raw data. Thank you. Hey everyone.